Hello everyone, my name is Shirota, and in this video, I'm going to talk about one of the subchapter in chapter 15, which is 15.4 double integrals in polar form. Uh, so the content for this video, I'm going to talk about three ideas and then I'll give one example. The first idea is concept and connection. This here I basically talk about double integral and what is it used for, and then make connection to double integral in polar form. And then I'll talk about Cartesian and polar conversion. This part is something we have already learned, but it's just a small review, and then I'll talk about how to use polar form in double integration and double integral to help you deal with some specific region. And then lastly, I'll talk about area in polar coordinate. And then at the end, we'll do one example. So now let's start with the first part of our presentation, which is concept and connection. So for concept and connection, as you have learned from 15.1 and 15.2, you know that double integral in Cartesian coordinate usually is interpreted as volume, right? And what about in polar form? Well, in double integral in polar coordinate is no different. It is interpreted as volume of solid over the region R. However, the special thing about polar coordinate is that it deals with specific region. What do I mean by specific region? So in 15.2, we talk about double integral in Cartesian coordinate and we deal with general region. We can basically use double integral with any kind of region. However, with specific region, like I'll talk about later, those specific region, if you use polar coordinate or polar form, it would make your life a lot easier. So what are those regions? Well, polar form allows us to deal with region that has rotational symmetry. So region that has rotational symmetry, such as a circle, cardioid, lemma cone, rose curve, demonstrate, etc. So whenever you sketch your region and you see that it has rotational symmetry on one of these dimension, you should probably try using polar to make your life easier. So now that you know the concept and you know the idea and why you should use polar coordinate, let's move on to the next point, which is Cartesian and polar conversion. So for Cartesian and polar conversion, as I have mentioned, it is something we have already learned. For example, is how do you convert from Cartesian to polar? Well, you use one of these formula, x equal all cosine theta or y equal all sine theta. And if you want to convert from polar to Cartesian, you use one of these, use both of them from time to time, depending on the situation, obviously. So all square equal x square plus y square, tangent theta equal y over x. These are the formula that you will need to use to convert back and forth between Cartesian and polar. So now that you have you know how to convert between the two, let's look at how you utilize polar in double integral. So how to use double integral in polar form? So obviously, when you do double integral, it is always a good idea to sketch your R. So for example, if your R is this circle, x squared plus y squared equal 4, for example, and as you can see, this area or this region of your double integral has rotational symmetry. It's a circle. So you should use polar here. So if you decide that you want to use polar, so how are you going to use it? Well, first thing first, you have to convert the region to polar. So you have to convert this x squared plus y squared equal 4 into its polar form. And we know that x squared plus y squared is all square. So all square equal 4, all equal 2. So all equal 2. So next thing, you will have to find the limit of integration in term of r and theta, right? So in order to do that, you should draw a line from the origin cutting to the r. So something like this. And then when you draw that line, take note of where the line enter and where the line enter and where the line leaves the r. So in this case, it starts at origin and it leaves at r equal to. So our R here would be, our R here would be from 0 to 2. And next, we'll talk about theta. Well, theta, you have to find the smallest and largest value that bound the region. Most of the time, you can assume that this positive x-axis is theta equals 0, and then you swap it counterclockwise to see where your data is, your smallest and your biggest value of theta. So from in this case, if you consider x-axis as 0 degree, then when you swap through, you have to swap one round, which is from 0 theta to 2 pi. So this would be your new region, right? Your new region in polar form. And then after you convert everything in convert all the region into polar form, you still have to convert one more thing, which is the function itself, right? So the function originally start off as f, x, and y. So now you have to convert it into f or theta. So far we have convert or, we have convert all, we have convert f, x, y, we have convert f to all f or theta. What about dy and dx? Well, for dy and dx, when you convert it into polar form, remember it's not just d or d theta, it's or d or d theta. So they are going to be or d or d theta always. And another thing to note in polar form, uh, your d or d theta doesn't switch, unlike in Cartesian. In Cartesian, you can switch dy dx or dx dy, but in polar form, you stick with d or d theta, and of course, don't forget your or. So now that you know how to convert or how to use double integral in polar form, let's talk about one last concept, and then we'll talk about an example. So the final concept of this chapter is the area in polar coordinate. So for area in polar coordinate, it's the same as in 15.3, where you find area in Cartesian coordinate. So if we were to have were to have this equation, we have to have this formula for our double integration in polar form. All you have to do to find the area is to let f or data equal 1. So when you do that, you would find the area of the region instead. What I mean by this is that normally when you find V, you are finding the volume of the solid, of some sort of solid above this, like some sort of solid above this region or. But when you let that f or theta equal to 1 and you get the area, you're actually finding area in 2D, in 3, in 2D, yeah, in 2D. So you're finding area, you're finding this circle area right here. You're just finding this area. You're not finding some sort of value, and you're finding something that you can actually see right now. So yeah, those are all the concepts. Now we'll look at one example. So for example, it asks us to change the Cartesian integral into an equivalent polar integral, then evaluate the polar integral. So in order to do that, obviously we have to sketch first. So to sketch it, we know that y is from 0 to 1, and x is from 0 to square root of 1 minus y squared. And if we were to sketch it, y equals 0 is just the x-axis. Y equal 1 is, let's say, something around here. Obviously, this is not to scale, but okay. And then let's about x. X equals 0 is just the y-axis. X equal this part. If it's not obvious to you, this is a circle, but if it's not obvious, you can do this. X equal square root of 1 minus y squared. So it's x squared equals 1 minus y squared. So x squared plus y squared equal to 1. So this is just a circle with radius of 1 and center at the origin. So you draw a circle. It's not the most beautiful circle. This is our 1. So this is not the region we work in. We are not working with the whole circle. We are only working with this small area of the circle right here, because y from 0 to 1. So we're working, so it is this strip. And then x is from 0 to the circle. So x is this y-axis. X equals 0 is this y-axis. x equal to the square root is this part of the circle. So we're just working with this area of with this region. So what about but after we sketch, we still have to convert this, right? So x squared plus y squared equal 1. So it converts into polar, it's all squared equal 1. So it's all equal 1. So this circle is all equal 1. So our region in terms of polar, your all, if you were to draw a line from origin path through all, your all will be from 0 to 1. And theta, if you were to swap it starting from x-axis, you swap it, you don't have to swap it all the way. You only have to swap it until the y-axis, which means that your theta is from 0 to pi over 2. So now you have this new region in polar form that you can work with. Let me change the color. So now let's say this is V. So our new V is, oh, there's another thing that you have to convert this x squared plus y squared. So this x squared y is just all squared. So it's all squared. And dx dy, as you know, you have it's r d r d theta. Now that you have that, our region, we know that it's always from 0 to 1, theta is from 0 to pi over 2. So now it's something that you can do. So you're able to do this quickly, 0 to pi over 2. So integration of all cube is 1 over 4 or to the power of 4 from 0 to 1 d theta. And this one is just 1 over 4, right? It's just 1 over 4. So integration from 0 to pi over 2 of d theta is just pi over 2. So our answer is pi over 8. So this is one example of how you do it. And also that's the end of my presentation. Thank you for watching.